Okay, I don't particularly like taking a video of myself, but we're going to do this for a couple of minutes so I can show you some of the pieces of paper. You do need your cheat sheet out. You need the CI confidence interval chart out. It might be nice to have that handwritten summary. And throughout the video, I will be recreating the notes, but you can print the notes from video number 2 file if you want. So we're making the transition from sampling distributions to confidence intervals. Sampling distributions were what I called fantasy land, that all of those problems gave you the population truth, whether that was mu or p. Then it said we're going to take a sample and give you a sample size, and then it asked a question about the sample mean or sample proportion, depending on which one we were doing. So that was all handout 9, number 1 through 8 stuff. Now we are completely reversing. We are to real life now, confidence intervals. Confidence intervals say, well, we don't know what the population truth is. So how about that we take a sample? But we've already talked about how when I take one sample, I have no idea how sure I am about that one sample. If you go back to the intro before spring break where we did Jay, Teresa, and Kyle, I have no idea when I get a sample if it was a little below the truth, a little bit above the truth, or if it was pretty close. So there's got to be something better, and that's what a confidence interval is. We start with our sample, but then we're going to plus and minus a certain amount, and we're going to have an interval of values. Then we're going to be able to state how confident we are in that interval of values. I will write all of this on the board. It's also going along with the notes. Confidence intervals are very real life, and you're going to see that more and more over the next, 6 to 8 months as the elections come up. So I do want to start with an intro to show you that confidence intervals are on our TV, they're on the internet, etc. Most of the general public don't know that they're supposed to be doing a confidence interval. So because time is a bit tight, I pulled a graphic from a few years ago before the last presidential election, and I want to start with that. But maybe to kind of get a little more organized, we are doing the confidence interval for the mean in this video. Video number 3 will be confidence interval for the proportion. So we still have both camps going on, just like you had to work through when you were doing handout 9. So we have 2 different confidence intervals. They are both on test 3. This is the topic that you do actually like. It's formula based, calculator, shortcut based, with, of course, some interpretation, but the interpretation is usually not very hard. So again, on this little handwritten sheet, it kind of summarizes what we're going to be talking about here. Please read that later at the end of the video. We'll put that away for right now. On the cheat sheet, because there's a lot on here, most of this is test 4 material. But what we're doing today in this video says one mean, and it says confidence interval. So there is the formula right there that we're going to be introducing you to today. Okay, so you don't have to memorize that formula. All right, we'll put that away. And just briefly, I want to show you one more graphic that actually one of my students sent me. The idea of when we take a sample, we have no idea how sure we are of it. So this would be a misleading graphic, just showing you what the 2 samples are and saying, hey, there's definitely a difference between the black and the white. you have no idea how sure you are about those numbers. What we're doing today is actually going to be using something called margin of error, where we don't know that the top of the white bar is necessarily there for the truth. It's somewhere in this interval, and the black is somewhere in that interval. So if you ever see these little bars on a scientific graph, it's indicating the margin of error. I'm going to show it to you a little bit differently in a political poll in just a second. But while we have this graphic, again, I'm not sure that you can see that little black bar right there, but those black bars indicate the confidence intervals. Those black bars are overlapping each other. So actually, this is a graphic that is indicating you cannot tell a difference between the black and the white. This is misleading. This is indicating there is a difference. This is the truth, and we do not know if there's a difference. All right, I'm going to turn this around to my whiteboard. So formally getting to the notes now. Again, you can have this printed or split your screen. This was a graphic that I found from a few years ago. Basically, it says that Trump was sitting at 48% and Clinton was sitting at 45%. Now, I absolutely guarantee you, when whoever was talking about this graphic, they absolutely indicated that Trump was in the lead. They probably talked about what Clinton had to do to catch up to Trump and what Trump had to do to keep his lead. That is actually not the case at all. If you look very closely at the side, normally it's written at the bottom. This one is written on the side. It says the error is plus minus 3.5%. These were numbers that came from one sample. I'm assuming it was the standard 1,000 registered voters or whatever. We have no idea how sure we are about the 48% and the 45%, but we can build an interval of possible values using this margin of error. So Trump, I'm going to just plus or minus 3.5 from each one. I think I'll cheat and look at my numbers. 44.5 to 51.5%. And Clinton, I'm going to plus or minus 3.5 from the 45. Again, we will get to formal notes in a minute. This is just some intro to show you that this is actually a confidence interval problem that you would see on television or on some internet news website. And the people who talk about it probably don't even know what they are talking about. So now I see that I'm 95% confident of these intervals, that Trump is sitting somewhere between 44.5 and 51.5. Clinton is sitting somewhere between 41.5 and 48.5. Meaning, let's say Trump was up at 41 and Clinton was down at 42. Then we could predict that Trump would win. But look, Trump could be at 45, Clinton could be at 47 or 48, and that would indicate that Clinton was going to win. So, part of our interpretations for this video and the next video will be when the confidence intervals overlap, you cannot tell a difference. Since the intervals overlap, you cannot tell a difference. Thus, we have no idea who is in the lead. It is too close to call. So, my issue is they should never put this graphic with the big numbers, and it even says Trump leads. That is actually a lie. They should just come on and say, okay, current polling tells us it's too close to call. Let's just talk about each candidate and what they need to do to win, or something like that. But when they stick this where everyone can see it, they really are lying to the American public. Most good graphics do give you the margin of error. It's just that most people don't even know to look for it. And if they see it, they don't know what to do with it. This is obviously talking about proportions, right? Can't proportion, are you going to vote for Trump or not? Yes or no. But it's probably what we see the most in real life. Now I'm going to switch back to give you the generic background notes for confidence intervals. And this video is going to go back to do the confidence interval for the mean. We will revisit confidence interval for the proportion stuff on video number 3. Let me get this erased. Even though I think most of you will print out my notes, some of you may not have a working printer since you're not on campus, and splitting the screen might end up being a bit cumbersome. So that is why I'm going to rewrite the notes on the whiteboard so you can always take notes by hand. This is in chapter 7. It's called confidence intervals. I'm going to write and then I'll read it to you. We don't know if our sample mean, our X bar, for example, is correct or even close, of course, to the population mean. Instead of just using one sample, it is better to build an interval of possible values. We can then state our level of confidence. Just to let you know, the default is 95%. Most problems you do for me are going to range from 90% to 99%. Basically, you could think about it in the opposite way. 95% of the time, we're going to end up being good. 5% of the time, we're going to end up screwing up. So the flip of that is what we call our error rate. Let's talk about the general form of confidence intervals. By the time we get through test 4, we will end up doing 4 different confidence intervals. Estimate plus or minus the margin of error. This is exactly what we just did with the Trump-Clinton. The estimate came from the one sample, that was that 48 and 45 or whatever. Then the margin of error, which needs to be stated to do good statistics. This is how it's presented to you on television. But how did they even know in that last example that the margin of error was 3.5% or whatever? Well, someone calculated it from statistical formulas. So So estimate plus or minus z times standard error. These are our z-scores that we've been doing for months now. Standard error, just to let you know, I call it standard deviation. They're synonyms of each other. And this is why we studied sampling distributions. These standard deviations are going to be coming from the results of sampling distribution. You need sampling distribution to understand confidence intervals. All right, I'm going to give you a few more generic notes, and then we're going to build our confidence interval for the mean and practice 2 problems. I'm going to erase now. Let's talk about what that 95% confidence even means. If we say we are 95% confident, this means 95% of all samples taken will end up building an interval that contains the population truth. 5% will not. Now, with that said, well, let me rephrase that. So we talked about with sampling distributions, you go get all possible samples of some certain size, right? So that's what this is saying. If you get all those different, for example, X bars, then you build the confidence interval, you jump up and down that margin of error. So you have, my hands are representing, the range of numbers. Then 95% of those would actually capture the population somewhere in there. We don't know if it's going to be towards the low end, towards the high end, just somewhere in there. 5% will not. Now, with that said, when you get a sample, you never know if it's going to be part of the 95% good ones or the 5% bad ones. So that basically means we're going to be wrong 5% of the time. If you are a book person, there is a nice picture of this, I think somewhere around page 297. All right, let's build our confidence interval for mu, the population mean. So in chapter 7.1, they build the initial confidence interval is going to be CI from now on for mu. Okay. Our general form said estimate plus or minus. If this is the population mean, then we use the sample mean as an estimate of the population mean. So X bar plus or minus, the formula says we're supposed to do Z times the standard deviation of X bar. Think back to video, before break. Standard deviation of X bar is sigma over square root of n. So hopefully that looks familiar and that you've been using that a lot in homeworks for handout 9. Now, here's the problem though. This is fantasy land. This is why I don't assign problems from chapter 7.1. This is not real life. If I don't know what the population mean is, why in the world would I think that I know what the population standard deviation is? I wouldn't. So this is not real life. We need to tweak it. So we're jumping straight ahead to chapter 7.2, the real life formula. I'm about to throw out some letters you're not even supposed to know what they are yet. T times S divided by square root of N. Now that makes sense because I said I don't know what the population standard deviation is. Okay, what could I use as an estimate for the population standard deviation? I'm going to use S, the sample standard deviation. S estimates sigma, right? Well, then what's this thing? See, since I'm doing another estimate in here, I get nervous. And when I get nervous in confidence intervals in statistics, remember how we're trying to make an interval of numbers? And if I'm a little nervous, I want to make it just a little bit wider to grab a few more numbers in there to kind of cover my butt, I like to say, because, you know, I'm getting a little nervous. So, first of all, let me put a box around this. This is the formula that we are using. This is the formula that is on the cheat sheet. But what is this T thing? Now, if you've had AP Stats, you probably studied the T distribution for an entire class period. We're not going to do that. I'm going to give you highlights for about 2 minutes because basically what we need is, I've lost my sheet, is going to be coming off the CI chart. So I need to erase. So just a little bit about what this T is. The T distribution is very similar to the Z distribution. It's unimodal and symmetrical. Basically, T's are a little bigger than Z values. What has that got to do with what I said a few minutes ago? That I get nervous and I wanted to make my interval a little bit wider. Well, think about it. Let me put my formula back up so I can point to things. If this T is a little bit bigger number, then that means I'm plussing and minusing a bigger number. So if I'm here, and if I'm plussing and minusing a bigger number, I just made it wider. So that makes my confidence interval just a little bit wider. The only thing that you need to know in order to use our confidence interval chart is something called degrees of freedom. We're not even going to talk about what that means. It's DF for short. By formula, it is sample size minus 1. You don't even have to memorize that because that is on the cheat sheet also. One other little comment. Oh, that looks terrible. As your sample size, that's an N, sample size, increases, the T values actually get closer and closer to the Z values. I want to come at this intuitively. If I have just a ton of data coming in because I increased my sample size, then I'm not as nervous, right? And that's why the T can get smaller and smaller back to what it should have been. While we're here, when we go to our calculator in a few minutes, this is going to be the shortcut. You do have to memorize where it is. For test 3 and test 4, we're going to be going to stats and then test a lot. This one that goes with this formula is called the T interval. Do not pick Z interval. It's the T interval. When you get there though, and we're going to practice this in a couple minutes, it's going to ask you, do you have data or do you have stats? If you put data into L1, then you're going to pick the data option. If you just have been given X bar and S, then you'll pick the stats option. We're going to practice one of each of those. Our calculator is going to spit out the confidence interval to us. Super simple. One thing that might annoy some of you guys, though, is I never want you to become TI-83 dependent. So I'm always going to make you show me the setup of the confidence interval, meaning all the numbers plugged in. Then we're going to go to our calculator, use the shortcut to, quote, get the answer. Then we'll do some interpretation. So let's do an example or two. Okay. This was a stupid problem from a very formal textbook. So I always do it so I can pick on the problem. This was about families and doing housework around the house. They said there were 50 moms. Their average minutes of housework was 45 minutes with standard deviation of 5 minutes. They surveyed 20 sons. Their average was 12 minutes and their standard deviation was 7. Then they surveyed 26 daughters. Their average was 14 minutes, and their standard deviation was 8.6. I've always found this amusing because I don't know where the dads are. These people are not necessarily part of the same family, so don't overthink that. We are going to make 95% confidence intervals for the true mean housework times for each. See, here's the thing. We know what the truth is for the 50 moms, but I want to make a statement about all moms, the population of moms. So remember, these numbers are just for those samples. We have no idea how sure we are about these numbers and how they relate to the population mean time. That's what our confidence intervals do for us. Let's set up all 3 of them using our formulas. Then we'll take time to go to our calculator. So for the moms, I'm supposed to do X bar plus or minus. We'll come back to that T in just a second. Just leave a little space. S over square root of n. Okay. Sons. X bar plus or minus. I'll come back to the T. S over square root of the 20 sons. And then the daughters. Daughters, X bar plus or minus. I'll come back to the T. S over square root of n. All right. Where do we get those T values? That is what this chart is about. If you look across the top, that gives you the level of confidence. For this problem, we're going to be using the 95% column, Okay, so we're going to be in here somewhere. Remember this, if you can't read that, it says T, critical values. Degrees of freedom, that's n minus 1. So for the moms, n is 50. So technically degrees of freedom is 49. This is a skimpy chart. You're not going to be able to find 49, so you're welcome to go with the closest or to split it somewhere between 2.02 and 2. You can use 2.02 if you want. I'm probably going to use 2.01. So either one of those would be fine. Sons, n is 20, degrees of freedom is 19. Pause me, go see if you can look up the correct number. You should have found, for degrees of freedom of 19, under the 95% column, 2.09. Daughters, n is 26, degrees of freedom is 25. You should see 2.06. Okay, so this is what I require when I say show me the setup. Now we're ready to learn the calculator. So again, if you didn't bring your calculator home, I was able to download an app that looked like that, but in order to do the shortcut statistical functions, I think it was going to cost $5. I have my calculator, so I did not have to do that. Some of you guys might be able to find a TI-83 online app, whatever it takes to be able to practice these shortcuts. All right, so you're going to go to Stat. Well, turn on your calculator. Going to go to Stat. We used to go to Calc a lot, but we're going to Test now. All right, these first 6 or whatever are really Test 4 material. See where it says Test? That is not what we're doing. We're doing intervals, so you need to scroll on down. Do not stop at Z interval. Go to T interval. It's number 8 on mine, T interval. Hit enter. Now it says input. We did not type in data into L1. You want to make sure you go over to stats. Move over. You have to hit enter. Then the whole screen will change. It is asking you, what is X bar? We're going to do the moms together. It's 45. What is S? For the moms was 5. The N was 50. C level, 95. If you have a Casio, you have to put in the C level as 0.95. But all of the TIs will handle it as just the number 95. And then hit calculate. CIs take a few seconds to calculate. There is your confidence interval, and it reminds you what you actually typed in. Make sure I did that right. Oh, I don't even, yes, I do have the answers. This is my answer for moms. Pause the video. You go do sons or daughters, then come back to make sure that you did it properly. Okay, so those are our 3 different confidence intervals for moms, sons, and daughters. Formula-based, calculator spits out the answer. We do not need to calculate all that stuff by hand because we're using the shortcut on our calculator. There are going to be interpretive questions. So we're going to practice that now with this problem. So I'm just going to kind of erase the top part. Let's see. Maybe I'll write, this was mom, this was son, and this was daughters. Okay. To clearly, shortly, succinctly answer confidence interval interpretive questions, I'm going to show you the shortest, simplest way to answer them. If you start to ramble and go rogue in your interpretation, you're probably going to end up saying something wrong. So let's ask some questions. So they usually start off of, based on your confidence interval, is there evidence? Part A. Do the daughters do more than sons? Meaning, do they spend more minutes on housework? So our daughters were here and our sons were here. This is just like the Trump-Clinton example that I did earlier. If you see the daughters and the sons, their confidence intervals overlap. They share some of the same numbers. If that confuses you, you could kind of picture like a number line. Sons is here, daughters is here, and see how they overlap in the middle. They share some of the same numbers. So when your confidence intervals overlap, that's actually the quickest answer. All you have to say is no. There's not evidence the daughters do more than sons, because that was the question. No, because the confidence intervals overlap. We cannot tell a difference. The girls could be up at 17 minutes and the boys at 9, and the girls are doing more. Or the girls could just be at 11 minutes and the boys could be at 15 minutes, and the boys were doing more. So that's what we mean by overlap. Back to this just for a second for the sons. Remember, we don't know where the truth is in there. We're 95% confident that this range of numbers captures the truth, but we don't know if it's closer to 8.7, we don't know if it's closer to 15.3, so it's just in there somewhere. A lot of students think the middle of it is somehow special. Think about what the middle is, though. Remember how we actually made that formula to begin with? We said x bar plus or minus da-da-da. X bar, the sample mean, is absolutely the middle of your confidence interval anyway, and we've already talked about how we have no idea how sure we are about the x bar. So there is nothing special thinking that, oh, the truth is probably in the middle. That is false. The middle of the confidence intervals, all of these, is that x bar, and we don't know how sure we are about the x bar. All right, let's do a part B. Is there evidence that moms do more than daughters? So here's our moms, here's our daughters. Now let's talk about what you cannot say, period. You cannot simply say yes because the confidence intervals do not overlap. While that is a true statement, you're not telling me who's doing more housework. I'm going to come back and say, oh, did you mean that the daughters are doing more than the moms? So this is how you clearly have to answer it. You're going to see me use that word entire a lot. So, is there evidence moms do more than daughters? Yes, the entire confidence interval for the moms is greater than the confidence interval for the daughters, meaning every single number in the mom's confidence interval is, in this case, happens to be bigger than the 17.5. That is a complete answer. We got two more interpretive questions here. So I'm going to erase my A and B. So parts A and B were how to compare two confidence intervals. Parts C and D are going to be how to compare one confidence interval to some number that they're asking me about. So, is there evidence that daughters do more than 10 minutes? Well, we see the daughters' lowest value is starting at 10.5. See how this entire confidence interval is greater than 10? That's probably the shortest, cleanest way to completely answer the question. Yes, the entire confidence interval is greater than 10. Some of you would now ask me out loud, can I say it like this? Can I say it like that? So I'm going to have to handle some of that through this video. You could say yes, the entire confidence interval, or something like yes, since the confidence interval starts at 10.5, that would be fine also. What about this one? Is there evidence that daughters do more than 11 minutes a day? Okay, now remember, our daughters is 10.5 to 17.5. Confidence intervals, though, are entire little packages. You're not allowed to talk about, oh, well, most of the confidence interval, or some of it, or a lot of it. Confidence intervals are very black-white topics. The entire thing has to do whatever you're being asked. Every single number in here has to be greater than 11 in order to say yes. And that is not the case. So the answer is no. The entire CI is not greater than 11. You could say no, since the CI goes down to 10.5. That would be perfectly fine also. You just have to remember, and it's on my notes, so maybe I should put it up here. The entire confidence interval has to do what is being asked in order to say yes. You never want to talk about most of it or it's really close. Those are all wishy-washy words. The pickiness of interpreting confidence intervals is not my pickiness, period. There I go again with my voice texting habit. Ha. When we get to test 4 and we do hypothesis testing, Hypothesis testing and confidence intervals support each other, and hypothesis testing are extremely specific and particular and picky. So we need to learn the precise interpretations here to be able to support our test 4 material. Let's do one more problem, how to deal with if they actually give us a data set. Right, let's see. I made up this data, but let's say, cans of soda are supposed to have 12 ounces in them, but we've already talked about tolerable limits and quality control. So let's say they actually measured how much soda was in a sample of cans. We'll keep this data set short so it won't take you long to put it in your calculator. I just need to state normality because all of those normality assumptions from sampling distributions on handout 9 have to be part of confidence intervals. I'm not going to have you test it in confidence intervals, but I absolutely will have you test it for any type of handout 9 problem. Okay, let me get my data set. Two, four, six, eight. 8 data points. Pause the video. Type those numbers into L1 on your calculator. We want to make a 95% confidence interval for the true mean number of ounces, meaning in all cans of soda. Now, I can't even really set up my formula yet because I don't even know what X bar and S are. So whenever you're given real data, you have to go to the calculator first. So you put your data into L1. Now go to Stat, Test, go find your T interval again, move left arrow over to Data, make sure you select it, and it's going to ask you, where did you put your data? I'm sure you put your data in L1, second of 1. Don't worry about frequency. It should say 1. You should never have to change it. Sea level 95. And then hit calculate. When you do that, you're going to see your confidence interval. And then you're going to see everything that you need below it in order to set up the formula. You should see that your X bar is 11.95. We'll come back to that T value. You should see your S is 0.207. And then, of course, our N was 8. Very small sample size. We're still at 95%. N is 8. Degrees of freedom is 7. So you should see the number 2.37. Remember, this is coming off your CI chart, that 2.37. Okay, that's your confidence interval for the population mean number of ounces. The 11.95 was just for the 8 cans. This is a statement on the population of cans. Let's ask one interpretive question. Is there evidence there's more than 11.9 ounces? Is there evidence it's more than 11.9? I purposely made it really close to get you out of a bad habit. You cannot say, oh, most of it is. The entire confidence interval has to be greater than 11.9. So the answer is no. The entire CI is not greater than 11.9. You could say no because the confidence interval goes down to 11.78. That would be fine. I'm going to erase, so pause it if you're not caught up. I want to give you your homework now. You should be able to do handout 11, one through 4, and 8 through 11. Practice all of those first before you come back and watch video 3. Video 3 will be confidence intervals, going to be very similar, except that we need to deal with the camp proportion, the yes-no questions, political polls, things like that. All right. Email me if you have trouble.